My name is Jeff Baker. I'm an electrical engineer with March Consulting Associates, and I've been asked to do a series of 3 presentations titled Safety for Electrical Engineers. I've been working in the field for 18 years or so, and along the way completed a master's degree, project management professional, all those other acronyms after my name, and had enough experience with the various sites around that university has asked me to prepare a presentation to help with students and their safety around electricity, or in general at these sites. Now, really what we're looking at covering today is just a few quick topics. I'm going to be looking at the importance of safety, the expectations of society. A lot of people get into the engineering field because of the high focus on science, math, and technology, but something that you'll learn as you hit the registration level for your professional designation, or even hopefully throughout your university career, is that the reason engineering exists as a discipline is to provide that extra layer of safety for society. If a city wants to build a bridge, they need to know that that bridge is not going to fall down. They can't just go to just anybody off the street and ask them to build that bridge. There's a lot of science and safety expectations in that design, and that's where the engineers come in to do the math, do the analysis, and say, not only is this the only not only are these 5 options the only ways to do it, but these are the only ways to do it safely so that it won't fall down in 100 years or whatever the expectations are of that bridge, barring any maintenance and studies later to improve its life expectancy. We also look at risks associated with technological change, fundamental safety concepts, and hierarchies of safety controls. So, why are we here today? We need to be able to have a broad array of knowledge in various aspects of our design. You may be designing a power pole, power distribution system, but you may be thinking, oh, that's all electrical, that's all power, but the poles that hold the cables up, there's structural, there's mechanical, there's civil, there's all aspects of engineering are involved in the safety of any one system. So the goal here is, when we get out into the field, you may be in a situation where there's 1-2 engineers and entire teams of contractors and clients waiting on answers. We have to work as teachers, leaders, and workers in these situations. And some people in the class may go on to become industry captains, leaders, electrical workers in the power industry. Some may become members of different industries, and may even completely despise electrical work in general. Some may go into information technology, electronics, but the point is that safety is in every one of these disciplines to varying degrees. If you're working with a cell phone, it's a very low power source, but you've got a lot of potential for batteries to explode, electronics to burn out, and it may not, in that small cell phone, you don't have a whole lot of power in this, but the cell phone, somebody may sleep with it right next to their bed, may have it in their pocket, take it on an airplane. If it explodes in these situations, it can start a fire, burn somebody. It's not a lot of power there, but it's still a safety issue. And in today's world, electric power drives everything. Electronics are present in almost everything we do. If you think about computers, information technology, instrumentation, lighting, communication, heating, cooling, robotics, transport, process control, industry, medicine, they all involve electric power, electrical signals, electronic controls, electrical interlocks. Some of those terms you may not even be familiar with at this time, but you're going to learn them as you are out in industry. That last one I mentioned, electrical interlocks, that has to do with the very aspect of opening a breaker at very, very high energy levels, or think 230,000 volts. Just opening up the disconnect to shut the power off can be create such a massive arc inside of the equipment that it can cause an explosion in itself. And if all you're trying to do is shut the power off so that you can do some maintenance, do some construction, you'd like to do it in a way that's not going to cause an explosion. So the way that they do that is they use an interlock that they have to go to the breaker or the shutdown system. Once that is shut down upstream, they take a key out and they bring it down to the disconnect, put the key in, and now you can operate the disconnect safely because the power's gone. You might be thinking, well, what's the point of opening a disconnect if I've already opened the breaker upstream? Well, the disconnect allows you to put a lock on it and ensure that a worker downstream of that disconnect has put their own lock on it. They're the only ones who have the key. It's got a tag on it that says who's shut the power off and what they're doing downstream, how long they'll be working on it. And because they're the only ones with the key, they know that even though they're touching that copper line that could kill them, the power's shut off and nobody else can turn it on. Basically, it comes down to electricity being all pervasive and ubiquitous. Electricity has provided society with tremendous advantages and is a force for good if properly used and controlled. But it can be also very destructive if misused and not properly controlled. So this one is just I believe my old colleague who prepared the presentations before me found this picture online and found it as a excellent example of major safety concerns. This is only looks like probably a 220 volt plug, but obviously water and electricity don't mix, so something is very wrong here. With that in mind, there has been a great improvement in safety awareness in the modern workplace. However, as engineers, you will inevitably be faced with a dilemma. Should you call an electrician or a plumber in this kind of situation? Sometimes the proper solution is not always apparent, but don't overcomplicate things. In this case, turn the power off, shut the water off, and then call both an electrician and a plumber. Start looking into the solutions. So it is with most safety issues, use common sense and use the KISS principle, which, if you haven't heard the KISS principle, keep it simple, stupid, and you will find yourself in your career when a client calls you up and asks you to do, say, a small contract investigation for them over a couple of weeks, and you're trying to figure out, you'll go down the rabbit hole of looking at 100 different solutions to solve their problem. And at some point along those 2 weeks, that KISS principle comes in, and you'll start asking yourself, why are you looking at solutions that are extremely difficult and complicated when you could just solve it in one shot and not worry about it? That's the KISS principle. Don't overcomplicate things. Don't put 50 steps into a solution. Just find a way that makes it work safely and efficiently. Now, as I said on the last slide, there has been a great improvement in safety awareness in the modern workplace. However, today's workplace is still fraught with safety hazards, known, unknown, visible, and invisible. If we look at the top left, this is an expected hazard, but not noticed. This is a control circuit in a new hot water boiler. The manufacturer was aware of potential hazards from components coming loose during shipping. It's tagged with warning information. Let's see, does this show up? My mouse, can I point at things? Bing, bing, bing. Yes, I can. Perfect. Okay, so we're looking at this picture here, and you can see a tag. This tag is actually explaining, it's a warning that's explaining that during shipment, components could become loose and needs to be investigated by trained personnel to make sure that these components, these fuses, everything is tightened to manufacturer specifications. If anything did come loose, you can actually get small arcing inside of the connection, and then the small arcing over time creates heat and creates damage and leads to large arcing, which is a safety issue. Somebody's going to get hurt. In this instance, the contractor was so intent on finishing the job that he did not follow instructions on the warning, installed the system, and the next thing we know, it overheats and the styrofoam insulation starts burning. Results in smoke, toxic fumes. Emergency response teams called out, unnecessary hazards to fire crews and residents of the building, and ultimately results in a safety cost. Hopefully nobody ends up getting hurt, but the other side to safety is the costs of dealing with it later when it is a direct concern, rather than in advance when it's upcoming problem or a potential problem and nothing bad has happened yet. If you can deal with it when it's just got potential, it's cheap and much more manageable. In the top right, you've got a fellow working on electrical connections. This looks like low voltage, so he very well could be working on it live. He's sitting in a puddle of water, and he's clearly not wearing proper PPE for working in this situation. It's a known and visible hazard, but it's intentionally ignored. In this case, the worker chooses to ignore basic safety practice and proceeds to work on electrical wiring with his feet in the water while sitting on the wet ground. What safety precautions should this person have taken? Working in dry conditions, not always avoidable if there's an emergency power outage in the middle of a storm. Sometimes they have to work in wet conditions. Disconnect and lock out the power source. That's always something that is possible, and in fact, it's the number one rule at every safety presentation you will ever hear regarding electricity is disconnect and lock out the power source. It's sometimes not avoidable if shutting the power off means that the entire process fails and the company's out millions of dollars in equipment. That brings up a whole other aspect of safety we'll look at after here. And then the other one is working off a non-conductive surface. If you know the water is down there, put a board across, put a plank across, isolate yourself from the water, isolate yourself from the moisture around you so that you've got some additional layer of safety. The other thing he should probably be doing is wearing proper gloves, proper protective clothing, just ensuring that if there is any arcs, there is any sparks, that it's not going to burn him. And then this last one is invisible but should have been anticipated. What you're looking at here is a plug at home, an outlet at home with multiple levels of appliances connected to it. You can end up overloading your electrical outlet. The first time that a problem is noticed is when the installation starts burning, if someone is in the area. So what that's saying is, in your electrical panel, you've got breakers. When you plug enough equipment into it, the breaker should go off. It should open the fault. But if you're plugging just on the borderline of what's acceptable on that breaker in, and it's just the breakers take time to operate, so if you can push it just into its overload condition and pull it back and cycle it, you can get it to a point over time. I'm not talking about instantly, but over a significant period of time, where that's going to cause heating on the cables and burn things out. That's why it's never recommended to put this many devices hanging. The other thing you can see is there's exposed copper, there's exposed plugs. It's not, if you needed to put this many plugs in, this is not the safe way to do it, let alone the heating itself. Whenever you do overload a circuit, the house wiring or any wiring can overheat and cause a fire. As engineers, electrical engineers, we try to ensure that doesn't happen with breakers, safety devices upstream, but there's always ways to defeat the safety. Other hazards from electrical and appliance fires include toxic and noxic gases released from fire, like vinyl chlorides, styrene, and dioxins, for example. Something as an example from my own personal life, when my wife and I sold our first house, part of the purchase for the new owners was to have a CSA certified inspector come in and look at everything. I had changed some of the breakers around, added plugs over the years, everything to code, but when the inspector came in and looked at it, they actually found that the 220 volt plug from the breaker up to our stove, which I had never touched, it was there long before me, whoever installed it didn't tighten the lug tight enough inside the breaker panel, so the copper was making a connection. It's making a connection, but it was loose. So as it's, I'm not sure how much you can see that. Yeah, it's showing up. So as it's in there, there's a little bit of a gap between the lug and the copper wire, and it would arc in between them, which normal use, the little small arc like that, no big deal. But over time, that arc creates a localized heating, burns a spot in the copper wire, and every time it's arcing, it's producing more and more heat. You can actually start a fire from that, and if nobody's home, or even if you are home, you don't notice it because it's in your basement, it's put away in your mechanical room, nobody's down there looking for fire and looking around. Maybe you don't have a good fire alarm system. A lot of people don't even have one in their mechanical room, fire detection. You can actually end up burning your house down. And when the inspector told this to me, I was completely surprised. In fact, I was a little upset. I was like, an electrical engineer with a lug that's not tight enough? Are you kidding me? This is embarrassing. And I remembered that, well, one, I didn't do it, and two, well, I should be pretty thankful that he found it before anybody got hurt. We were able to go in and check the cable. The cable was fine, just damaged at that connection point to the lug, so we cut it back, trimmed it, reinstalled it, and now it's just fine. But little things like that, they add up over time. Our arcs produce enough power to burn copper given enough time. Even a small little arc like that. Big arcs, they'll destroy copper, but a little one, it certainly can. So here we're looking at a challenge of being an engineer. I said earlier, as you register for your professional practice, you write your exam, you go through your ethics training, you learn about the legal side of being an engineer, that everything comes back to safety. This triangle is talked about a lot. In this case, we're calling it safety triangle. I don't believe that's what it originally is called in whoever conceived it first, but for the purposes of this, we're calling it the safety triangle. What we're looking at is how society will constantly challenge you. As an engineer, we have to decide how to do the work safely, and the client always wants things done fast and cheap. They don't usually think about safety, and they don't usually think about the right way to do it. What the right way to do it means is our certifications and standards. As engineers, we are tasked with understanding and knowing the safety standards and regulations of whatever jurisdiction you're working in, and not just knowing them, but understanding them to apply them to the specific scenario, so that we are taking the responsibility that this design is going to be safe for whoever is working with it or working in that area, sitting in an office building, that the office isn't going to burn down, isn't going to cause the air to be polluted and infect people's lungs. So many different aspects to what we're looking at. So if you'll notice though, fast, cheap, doing it right is all linked with safety. And doing it safely is the one thing that is not negotiable. If a client wants it done cheap, and the only way to get it cheap is to sacrifice the safety of the system, it's not happening. It's not getting built. And there's examples of that very thing occurring, where a lot of times it's not called out as the reason, but governments will say, well, we went and did budgetary analysis, we got some firms to investigate, do a feasibility study for us, a pre-feasibility. They came up with a cost for the whole project of $30 million. That was too much. We only had a budget of 10, so therefore the project is shelved. We can't do it. Well, if you look behind the scenes, it could be done for 10. It's going to fall down after a couple of years and somebody's going to get hurt. That's where the engineers have told them, we cannot sacrifice safety. The cheapest you can do it that maintains safety and meets regulations is $30 million. Sorry, your budget's not going to work. You start saving up some money, because it's just not going to happen right now. Another aspect to safety is technological change. It's a quote from Mark Zuckerberg. Think about what people are doing on Facebook today. They're also building an image and identity for themselves, which in a sense is their brand. It's almost a disadvantage if you're not on it now. Facebook is maybe not as ubiquitous as it once was. It's still wildly popular worldwide, but it's not used in the same way it originally was. But it's certainly used by a lot of marketers to get themselves out there. But when change comes, when technological change comes, there's questions that engineers need to ask. Who is at the forefront of this type of technological change, and what ethical dilemmas come with this change. An example would be, part of electrical engineering is the IT industry, and it's enabled by the electrical industry. So you are all part of or will be part of technological change, whether you like it or not. Some ethical dilemmas as examples: sentencing software in the judicial system. Advanced AI is becoming more and more capable as development continues. Think about the semi-self-driving cars from Tesla. Ford has some, Google has some, GM. They're all over the place. They're touching on all aspects of our lives now, that AI. So think about sentencing software in the judicial system. If somebody goes in front of a judge, presents their case, is it okay for the sentence to be determined by a computer, looking at an analysis of past cases, removing biases? There's strong arguments for it, but on the flip side, there's strong arguments against it, because no two cases in the judicial system are the same. So the argument would be there should be some kind of a person involved in that process. Another one would be ransomware. I'm not sure if you're all familiar with that, but if you open up the wrong program on your computer and your computer gets infected, all of your files get encrypted, and a pop-up shows up that says, if you send Bitcoin of X amount to this wallet, we'll give you the decryption password. And it's happened to many people worldwide, companies, government agencies. It's a misuse of technology, but it does not mean that we should shut down all computers and servers worldwide. It just means that as engineers, when we're designing systems, we need to take these things into account. You need to think about how people are going to abuse the system. Another example would be something like the dark web. When the World Wide Web was conceived, it was originally done as a science experiment between universities, connecting them to share information. Now it's everywhere. We're using it right now for this very recording, and you're using it to attend the class at a later date even. But on the other side of it, there's the websites that are not listed that people use to exchange goods, services, that are illegal and completely unethical. So do you shut down the internet? Do you not develop the internet because somebody's going to use it that way? Well, of course not, but you need to take those thoughts into account when you're designing your systems. Another quote, because quotes are fun. It has become appallingly obvious that our technology has exceeded our humanity. So something to keep in mind is, do not lose sight of our humanity. I implore you, as you become future leaders and innovators in our society, just do not lose sight of our humanity. It's sometimes when you're working as an engineer, you get this big new project, you're excited, there's a large budget behind it, you get to work in something you've never done before, you're looking at technology you've never worked with before, and you just want to dive in. But as an engineer, it's your responsibility to take that step back, look at the big picture, and say, okay, all these things are still cool, but if a contractor enters this area, are they safe? If they're not safe, is there a way I can change the design so that they are intrinsically safe? If they're walking in a switch yard for 230,000 volts, they shouldn't have to worry that substation is going to arc to them, their body, into the earth, killing them. They should be aware that there's a zone of protection, that cable is high enough in the air that they're not going to have to worry about getting arced. An excellent example of that from my own career, we were touring one of the mines in Saskatchewan many years back, and the electrician on site took us through their temporary construction switching substation, which was, I don't recall, it was over 100,000 volts. Oh, maybe it was 72,000. In any event, a lot of power, a lot more power than you'd ever see in your home. And when we were going through there, he was showing us that they had a lot of problems with the engineering design that was presented to them, because the cables up ahead, they're coming in, they're uninsulated, they go into some equipment, there's some isolators, there's a bit of insulation throughout, but for the most part those copper conductors are uninsulated. So the only thing you're relying upon to protect from arcs is that the physical distance, the space of air, how much the dielectric of air is before it breaks down, the resistance of air before it breaks down. And what the engineering firm had done, not our firm, but another one, what they had done is they had put metal stairs. The control box for this substation was up about 3 or 4 feet in the air. So what they built was a set of steel stairs that were embedded into the earth and grounded up those 3 or 4 feet. So now if you're they did the calculations, and they said if you're a 6'2", 3 person, and you walk up there, you're perfectly fine to operate the equipment that's directly in front of you. But what they also pointed out is that those people should not put their arms above their head, because as soon as they put their arms above their head, they couldn't guarantee that they were going to be outside of that zone of and protected. The electricians correctly pointed out that an engineering firm should have been aware of the fact that nobody wants to get any closer to that high power lines or high voltage lines than they need to, so put the controls down at user level so they don't have to go up. And 2, if there's no other avoidable way of then going up a few feet, maybe put it on a platform that isolates the operator from the ground, so that they're not a source or a path for that power to get to ground. So the company agreed, ripped out the stairs, and put in new wooden stairs so that there was some additional resistance between the operator and the ground level or earth itself, and they didn't become a conducting path for power in the event of a fault that happens directly through their body. So kind of some pros and negatives of technological change. We're learning new things, we're advancing and getting better access to information. Generally makes lives easier, safer, and healthier. Something as a simple example off the top of my head would be asbestos insulation. Asbestos insulation at one time was used, especially in Saskatchewan, everywhere. You'll still see it at the mine sites because they were built in the 60s, many of them. But as they learned later, asbestos causes, when it's moved, it becomes airborne and people breathe it in, and over time it creates lung cancer. So at the time it was seen as a cheap, readily available insulation source that was at a high insulation rating, and it was used everywhere. But the disadvantage was unknown potential future health effects. Technology is great, but it comes with risks that need to be analyzed before we implement it. That technology also can help facilities make better decisions, but some of the disadvantages is, if you get too much information, you're overwhelmed, and a lot of it may not be that useful. I say a lot, dang it. Social and political difficulties, instant gratification, unknown potential future health effects, safety problems, decision paralysis, which ties into too much information to be useful. If you're overwhelmed with information, making your decision becomes very difficult, and as engineers, that's one of the things we need to do, is to help guide clients towards the safe approach to whatever task they're trying to solve, whatever problem they're trying to solve. So looking at some more risks of technological change. It can bring about new hazards, increased accidents, new and unproven concepts, designs, materials, and health impacts. So new hazards, new technologies often bring up new and unknown hazards. For example, 30 years ago, who would have believed that cell phones could be a significant cause of highway traffic accidents? But today, cell phone use is so widespread and affordable that they've become a serious concern on the highways. Every day when I drive into work, I see at least one person with their phone held up to their ear talking on it. I'm assuming it's an important phone call, but it's probably not important enough to risk the lives of everyone else on the road, their own included. Pull over, use your phone safely. Another example is people stick earphones in their ears and listen to their smartphones. A few years back, and I believe iPhones were the first to do this, but a few years back the maximum volume setting on devices was much higher than it is now. Why? Well, because I'm going to try this. Scoliosis, hearing loss from social activity, is now recognized as a much greater problem than it was initially. Knowledge, to a great extent, is based on learning from historical events. Science is not about knowing the answer before you start. It's about developing and finding the answer, refining it, learning from the past mistakes, and building upon it. Sometimes we release the technology, and things like realizing that the max volume setting on the cell phone is too high, causing ear damage, hearing loss, you learn about it after, and corrections have to be made. But as engineers, that's what we're supposed to be trying to think about. New technologies require that we predict outcomes and hazards using various techniques such as predictive mathematical modeling and other methods that do not necessarily include experimental learning provided by history. If we can identify hazards before it's already caused damage and caused safety problems, that's what we want as the most ideal way. Often we must learn by doing and may have to adopt an adaptive management strategy, responding to surrogate indicators of a potentially greater hazard before the greater hazard actually manifests itself. The next one, the increased accidents. New technologies can often result in an increase in accidents until people are familiar with the technology and more confident in its use. If you're not familiar with a new piece of machinery, even if it's something that you've worked on for years, if you've worked on a forklift for years and the company buys a brand new one and it's got a totally redesigned control panel because loads of studies were done and it was found that control panel provides a much higher accurate controls, much safer, everything's improved, but you've never seen it before, you can be at risk of an increased level of accidents because you may not have entered it with the right level of training. And even though it was brought in to improve safety, in your instance it may not. These things need to be thought about. New and unproven concepts, design, and materials. New technologies often involve new materials, unknown concepts, and unfamiliar designs. We readily assume that if it looks, feels, and/or smells similar to the old technology, it is the old technology. This may lead to improper use, unrecognized changes in toxicology, different material behavior under stress, for example, resulting in unexpected safety consequences and/or health effects. That would be that asbestos example I brought up earlier would fall under new unproven concepts, design, and materials. They brought about new materials. It had great benefits in that it was readily available, it was low cost, and it performed very well. But they didn't know that it caused health effects and it caused other issues that were not proven at the time, which also ties into the health impacts. Potential health impacts are always a concern for a number of reasons. Impacts may only become known after it is too late, when the related disease already exists or the safety impact has already occurred. Health is an emotionally sensitive and personal issue and becomes difficult to deal with when compounded by these issues. Impacts may result in significant personal hardship. For example, contracting a debilitating occupational injury or disease. Asbestos. Disease and injury may result in significant financial cost to the individual, society, and industry. I took a class from American University one time I took a class from American University a while back covering their government administration groups, and they have a very different social protection, social net than what Canada does. But one of them that we studied was a fellow who was injured on the job, and his injury was covered under workers' compensation, and it was deemed, they came up with a path for getting him back to health and put together a recovery plan, And after the first year, working with the doctors, the nurses, all the medical professionals, they identified that getting this person back to full health was going to take the full 3-year plan that they had initially conceived, and they weren't going to get out of it. It was going to have to cost them a lot of money. So workers' compensation decided, that's too much. It's going to be a major financial burden to society. We'll just punt them off, which is probably the wrong idea, since they knew it was going to take 3 years worth of resources to get him back to health, and kicking him off of that plan meant that he was no longer going to have the safety net and the time to properly recover, and would cause major financial burden to himself and his family. But they kicked him off, and then a whole court case took off, and part of the class was studying that. But it's very important to understand, especially in Canada, where we have medical care for everybody covered by our taxes. When we get hurt, we go to the hospital, we take care of it. It's something we don't really think about. But if we're not being careful at work, then we're going to have an increase in the number of people getting hurt. And every time you're hurt, it doesn't cost you personally at all, which is great, but it does cost society as a whole. So now the amount of money that is available for us to make sure that everybody is safe and healthy goes down because you took an unnecessary risk at work and ended up hurt. And just, it's important to think of taking care of yourself, not just for yourself, but for your family, for everybody. Nobody wants to see you hurt, and just be careful. Alright, so some of the demands on engineers. I said earlier that the client usually wants things fast and cheap. They like it done right, but their first two goals are fast and cheap. So the demands on engineers is society as a whole accepts the benefits of all the technological change, but not all of the risks. Society is placing the demand on engineers to reduce those risks. Nobody wants to everybody wants to get that nice new cell phone. Nobody wants to see someone get hurt having that cell phone in their car. They'd like to see solutions to prevent that. Now, the obvious one at play right now in that case is legislative controls, but there are apps you can get for your phone that will track, and when you're in your vehicle, they'll disable it so you can't use it beyond hands-free mode. Something like that engineers would produce and put together to help improve that safety. Engineers require additional training in the following areas to meet these demands, such as workplace safety, due diligence, and product liability. Due diligence is a huge one that as you get into APEGs when you're done university, the APEGs being Association of Professional Engineers and Geoscientists of Saskatchewan, you will cover due diligence quite a bit. It's not just making sure it's done right, but having a proper record to prove that you did it right. If a fire happens and it turns out it was started in or around electrical equipment, you have to answer for it. How did that fire happen? Did you actually do the math to prove that your cables that you sized in that certain installation environment were correct? If you can prove all of that mathematically, you've got your records from the date that are stamped and sealed, signed, from the date that you did the design, then the investigators into the fire can go back to the contractors and say, okay, let's look at what you actually built. The engineer called for copper wire and you installed aluminum. You do realize that aluminum doesn't have the ability to carry as much current as copper at the same dimensions. And oops, that's where the fire started. Things like that, that's huge in due diligence, because it not only covers your butt in the event of a problem, but it also gives you that extra level of safety that you did when you're taking responsibility for the design, that it is actually done correct. And then this whole series of presentations is really intended to focus on safety in the workplace and give a little bit of insight into that workplace safety and what's required when we're at site. This one, we're looking at the incident and accident ratio theory. This is something that I mostly have to read off because there's a lot here. So Heinrich's work forms the basis for behavior-based safety, an approach that focuses on identifying and changing unsafe worker behaviors. Critics claim BBS, basis of behavior-based safety theory, right down there, point 2, emphasizes the worker's behavior without taking the system into account, the workplace conditions and/or management, a common argument aimed at Heinrich's theories. Statistician William Edwards Deming, whose work on quality control is credited with helping to turn around the Japanese economy after World War II, believed the vast majority of problems were the fault of the system or management, not the worker. Erickson holds that view as well. She cited a 2010 study from the National Opinion Research Center at the University of Chicago that found 85% of workers rated workplace safety as the most important labor standard. As workers ourselves, we accept that in order to live our lives comfortably and have a home and raise a family, we need jobs to earn money. We want to go to work so we can earn the money, but we want to come home so we can be with our family, and we want to come home safely. It makes sense that workplace safety is a major concern of anybody. These findings fit with Erickson's observations as a consultant and a safety manager, yet she was struck by the dichotomy between this finding and what Heinrich said. As a proponent of evidence-based interventions, Erickson's main critique is that Heinrich's work was not scientific. He used accident reports completed by supervisors, based his observations on retrospective data, and failed to investigate possible underlying causes. She said all he proved was a conclusion, and he primarily relied on the subjective observations of others, some of whom had a stake in blaming the employees rather than assuming any responsibility. This is what Erickson stated. So what this is looking at is the ratio of major or lost time injury, which would include deaths. For every one of those, there's 29 minor injuries and 300 no injury accidents, or we call those near misses. Somebody was caught doing something very unsafe but managed to get away with it without getting hurt. That's recorded, that's logged, because somebody needs to learn from that behavior, or that unsafe behavior. So something that there's a study that I read a few years back that directly relates to this, to Erickson's statement that she doesn't believe these numbers are accurate enough, and that's you'll hear about this when you're in your careers, the lean development model, lean theory of manufacturing. It was very popularized in Japan and has now spread throughout the world, and it's talked about a lot, how it's going to improve efficiencies and reduce costs and all these life-changing things that we should all start worshiping because it's amazing. They actually tried implementing it in Saskatchewan in our medical system, and the nurses complained that it ended up decreasing the amount of time they had to work with patients directly. It increased costs, and it wasted time during their day. So it did none of the things it promised to do. But the reason I bring it up here is Toyota was the one who originally invented this technique, and talking about that directly ties into Japan. They built high quality cars, and their claim was it was their lean manufacturing system. Well, there was a study done over the years that they had this implemented that found all of the corners that they cut, a lot of them were cutting safety corners, and in doing so, people got hurt at work. But yet Toyota's safety numbers, they stayed perfectly flat, no problems. Nobody had any extra injuries, especially none in the major or lost time injury category. And what the study found is what Toyota was doing is when people got hurt, they kept paying them so that there was no lost time, called it a minor injury. If somebody would lose their arm, I don't think that's a minor injury. They'd keep paying them, and once they were ready to come back to work, They'd have them come to work every day and put them in an office, literally an empty room, and you sit there, and that's your job, is to just sit there all day, every day. No phones, no computers, no toys, just sit there. And sooner or later, that employee will quit. Now you can say there was no lost time, there was no major injury, safety was very good, we only had a few minor injuries this year, and that employee quit on their own accord, therefore our system is working, which is completely against the safety regulations. If somebody's hurt ever, the safety officer's job on a site is to not represent the company, but to represent the safety and protect the employees. And it's a difficult position to be in because they're paid by the company, by the owner, but they have to represent true and honest numbers and protect people at the work site. So that was not happening there, and seeing this ratio, keep in mind that it may very well be higher. If a job needs to be done, there's some level of safety at risk. There's some level of potential for injury. If the system management, the design of what that work is to be, can be done differently, engineered differently, you can reduce that level of threat and give that worker a better opportunity to be safe. Earlier I brought up disconnecting lockout tagout of your power system. If you know that a power system needs maintenance, if you know that somebody needs to go in there, change some equipment, it's best to do that at a time when the process is shut down, power can be isolated, then the worker can go in, do what needs to be done, test everything out, close it all up safely, bring the power back online. As opposed to, earlier I said sometimes there's instances when live work needs to be done, and one of those instances would be in the middle of a process, and that load, a fault happens, it needs to be repaired, and if you shut down the power, the company's going to lose millions of dollars because the process didn't finish, and it's going to ruin all the equipment. Something like, think of molten steel inside of a large vat that's being moved between two sources. It's not heated when it's moved, so it only has a fixed amount of time to get there. If they have to shut the power off, they can't get it there, and that steel is going to harden inside of its enclosure, and now all of that equipment has to be thrown out, or at least cleaned and mitigate that damage. There's a lot of money at stake and a lot of time at stake, so they get an electrician to go in and work live. If you know that maintenance it needs to be done, or you know that fault has happened, and you can ride through the fault long enough to get that process into a safe place that it could be shut down, you do that instead of relying on an employee to go in and work in an unsafe environment. And there certainly are instances when employees are directly at fault. I don't know if this fits in best here, but one of my favorite examples of that would be during construction at a mine site. They had a significant lost time accident where a person broke their leg, shattered it, not just broke it, but the bones were shattered. And the way it happened is they were using a taper machine to, a machine that, lift my arms up a little awkwardly high, but if this is earth, the taper machine comes along and just pounds it down, compacts everything. And being at a mine site, this is no small one, it's a pretty hefty machine. It was brought to site on a trailer, secured, brought out to where the work needed to be done. It's a heavy, beefy machine. 2 workers are there working together, looking after one another. They did the work. As they concluded it, there's a second site that they needed to do the same work. So instead of putting the machine back up on the trailer, because that takes time and they want to get the job done, what they did is they brought a skid steer over, a small tractor, put the bucket on the ground, brought the skid steer over, brought the taper machine over, got her just onto the bucket, and then tilted the bucket up so it lifted it. And then, because that machine is 400 or 500 pounds, it's every bump they hit is potential for it to fall out. So one guy drove the skid steer, well, one guy rode in the bucket, and he held that machine, because boy, he's been hitting the gym lately. He can hold that 400 or 500 pounds, no problem. Well, it is a problem. It was absolutely unsafe and absolutely not approved. They hit a bump, and of course the machine went forward. The guy holding onto it tried to hold it, and he went with it, because there's no way that he can hold on to that much weight. And the taper machine ended up falling on top of his leg, crushing him, and he was out of work. Well, ultimately what happened, the two employees said that their manager gave them approval to move the equipment like that. The manager and the company that they worked for denied ever giving them approval. So those two employees cost their company their contract. The company got kicked off site and they lost the contract. The man probably will never walk properly again. He was a young guy. Probably no more sports for him unless it's low impact sports. No hockey, no football. Really, all the fun sports when you're young, gone. But it's something to keep in mind. It's not always the management's fault. They claimed that management said they could do it that way, but anybody who's using a machine like that should know better that you don't secure it that way. Whether somebody tells you to or not, just don't do it. Fundamental safety terms: safety, accident, danger, hazard and risk, hazard control. Alright, safety is a state of being relatively free from harm, danger, injury, or damage. Accident: an accident is an unintended, unplanned, single or multiple event, sequence of events that is caused by unsafe acts, unsafe conditions, or both, and may result in immediate or delayed undesirable effects. Two fundamental accident causes. Accidents are caused by unsafe events and/or unsafe conditions. Danger: inherent property of a system that has the ability to cause harm, may be physical, chemical, biological, socio-economic. A hazard is probability that harm will occur. For a hazard to exist, there must be a source, transmission medium, and a receiver. A hazard is an unsafe condition. And then risk. Risk is a measure of the likelihood and the consequence of all hazards of an activity or condition. And actually I lied. There's one more. Hazard control. Actions taken to reduce or remove hazard. Hazard control, especially at the design stage, is very big for the engineering profession, because that's where we can bring our input to prevent problems. You know, if a client is looking for a piece of switchgear that is cheap and gets them the job done, we can look at it and say, you know, the amount of power there, the amount of potential of an arc flash dictates that you should look at using larger switchgear that is arc flash rated and protected, so that anybody walking in the area has that extra level of protection. That's a quick example of the design phase where an engineer can provide that added value to safety. Some hazards of electricity. Electric shock occurs when the body becomes part of the electrical circuit. Electric shock occurs in one of three ways. Body comes into contact with the wires of an electrical circuit. That's literally somebody grabbing a conductor. Body comes into grabbing two conductors, I guess. The next way is body comes into contact with one wire of an electrical circuit, energized circuit, and the ground. Earlier we were talking about the electricians standing on the elevated platform in a 72 kV switchyard, putting their hands up. That arc that would hit their hands would go through their body into the ground. That would be an example of number two. The third one, the body comes into contact with a metallic part that has become hot by contact via or with an energized conductor. Example of that would be if a power line has fallen down and is making contact with your car, and you step out of your car trying to get away. That car is energized, and as you get close to the ground, you're going to the path is going to flow through you of that energy. Another example would be the equipment that you're working on, something's miswired, a fault has happened, and the enclosure itself becomes energized, which is typically supposed to be grounded, and you go over to open the door on the enclosure, and now instead of expecting a grounded zero potential door, you're touching some voltage, hopefully a small shock, but depending on the power level, voltage level inside of that enclosure, you could be getting a pretty good jolt. Arcing is the other hazard of electricity. Arcing occurs when current flows across two conductors that are not in direct contact, produces light as electrons move across the gap between two conductors. Arc is a function of voltage between the conductors, conductivity of the medium between them, and the distance between the conductors. Think of lightning. Anytime there's a storm, you see lightning, that's an arc in the air, a massive amount of power in a short amount of time, and it's broken down air. Air is the medium between the cloud and the charge in the air and the earth. It's a significant distance, but that air still breaks down and becomes conductive, at least in the path of that lightning. That's a large example of an arc. Earlier I talked about the stove and the breaker with the cable arcing inside of it. It happens inside of your home as well. So the hierarchy of safety controls. So the hierarchy of safety controls is looking at different levels of protecting workers. The most effective way to protect workers is to eliminate the hazard altogether, disconnect the power before a worker goes into that equipment to work. Substitute the hazard with a safer alternative. Instead of repairing this equipment, can we use a existing and already set up transfer switch to bring power from a different source? Isolate the hazard away from anyone who could be harmed. That would be if you are switching high voltage equipment. Even just switching a breaker has a risk of arc flash. So what's available for sites now is actually robotics. They'll put a robot in the electrical room. They remotely just use a control and drive that robot up to the piece of switchgear. The robot grabs the breaker and actuates it to disconnect power. That arc is going to extinguish inside, and if there is an arc flash, well, we're out a bit of money for that robot, but robots can be replaced and people cannot. So that's a way to isolate the hazard from anybody involved. Use engineering controls to reduce the risk. That would be something like the Kirk key or a keyed interlock that I talked about earlier, where somebody cannot operate a device until the power upstream has been disconnected, because that device is not rated to interrupt the power on its own. It's just an isolation method. So there'd be an engineering control that prevents anybody from unsafe behavior. And then there's the next one, which is administrative controls. That would be more along the lines of instructing workers not to do this. It's effective only so much as the worker is willing to listen, and management is willing to put the training in place and actually put faith in the safety systems. Sometimes you'll hear about management telling workers that I need this done now, go get it done, and they tell you, you've got 15 minutes, get this work done. But the worker knows that in order to do it safe, it's going to take me a half an hour. And management is screaming and yelling at them that they've got 15 minutes. So then they're going to go out and take a risk and avoid that administrative control. So it's not just the controls being in place, it's management putting in place the a culture of safety and believing in it. The management recognizing that I need this done in 15 minutes, but the only way to do it safe is 30, so we're going to have to adjust the delivery schedule. You go do the job in the time that you need to be safe. We'll go work on changing expectations of the client or whoever is waiting on that to be done, so that you can get it done safely and you're protected. The last one being personal protective equipment. I mentioned earlier the worker who was not wearing safety gloves while working with live electrical equipment. That would be an example of PPE, personal protective equipment. Now we got a short little video of an arc in action at a substation. Hopefully this is going to come through. I'll try and mute my mic for it. You'll see all the workers in the area. I don't know exactly the source of this video, but I assume that it was some sort of a controlled or expected event because nobody seems to be running. Whoops, I need that back up. But that would be that's what an arc looks like. Now imagine that happening inside of a metal enclosure inside of a building. That kind of an arc develops very quickly into an arc flash because there's other metallic systems around it, and it's enclosed. It's got nowhere for all of that pressure and all of that energy to go. So now it gets so hot that it liquefies the copper, and it explodes outwards at all angles until it finds a way out of the enclosure, and then it becomes a straight path. If you're a worker with the door open at the time, that straight path is coming right into your face, right into your body, and it's enough pressure that it will send a full-grown person flying across the room. There's a lot of power there. And this is a quick example of a single-phase short with some PPE as part of a test. Okay, what you're looking at, mannequin, obviously. It's a test system of some of the PPE. The worker has coveralls on. They've got a harness for working at heights because he's in a bucket. Helmet. Looks like there's a face shield here. And then we fire it up. Oh. Dang it. I wanted to pause it, not stop it. Okay, just look at how fast that happened. That was a single phase short, which means it's a three-phase power, ABC. One of those three phases is taken to ground. I assume this is a direct short, but in that instant, like we're talking, you blink and you miss it. It's so fast. The arc occurs directly in the worker's face, explodes, and extinguishes itself in that instant of time. Now we look at the mannequin after the fact. All the PPE is burning. The helmet is totally blown off. It kind of looks like there's still a face shield on. So I suppose the eyes are good, but I don't think the worker cares about that anymore. If this was an actual person, they're either dead or significant injuries. And in this test, this PPE was clearly not rated for the level of incident energy potential at that location. The correct personal protective gear should have withstood the heat and withstood the blast so that it would not catch on fire. That's the intention of it. But in this case, they're probably testing to a higher level of energy than what the protective gear is rated for, just to show what can happen if that's something people do as a mistake when they're working. So I guess another thing to think about is if you are going into an area with arc flash risk, make sure that your personal protective gear is properly rated. Now, that concludes the slides for today, but what I'll mention is going through all of this, it's important as engineers to understand not so much what we have to do to protect ourselves from electricity, but what we can do to protect electricians from being exposed to that fault. As engineers, when we go to mine sites, even mine sites that we've designed, all of the equipment that we're inspecting, we are not authorized, nor do we have any business touching or going inside of any of that equipment. We're not trained for it. Electricians are trained to work directly with the power. We're trained to design the power system, and there's a distinction there. I've heard of engineers getting fired and kicked off of sites for crossing that line between where you're allowed to go as an engineer and where you're allowed to go as an electrician, and that line is an actual physical line being somebody opens a bucket on an MCC and it's a live bucket, you can take pictures, but as an engineer, don't reach your hand in, don't be touching any of that live equipment. Not only is it unsafe to you, you're not trained for it. You probably are not wearing the correct PPE. I was at a site recently, and I was doing an arc flash study. I was asking for some of the ratings on the breakers. It was a 5 kV breaker, so it's behind a locked door, and I asked if we could get that rating, and the electrician with me, standing right next to me, walked over and put the hood on of a arc flash gear, nothing else, walked over to the equipment and started unscrewing it to open it up. And when a blast happens, it doesn't point itself only at your head. You need to be wearing all the equipment. Not only that, but I'm standing right next to him. All I've got on is your standard first level of arc flash coveralls. I have no idea how much energy is in that equipment. First thing I did is bolt to the end of the electrical room, so I was outside of the danger, and then I yelled down to him if he was sure he should be doing this right now. He took a minute and realized, oh, yeah, this equipment is all live. I don't even know if I'm authorized to open this. He went and talked to his manager and found out that if he had opened that door, it would have shut down all of site because it had a safety interlock that prevents people from getting inside of it with that much energy potential unless the power is shut off. So he probably would have gotten fired if he had done it. Thankfully he didn't, and nobody got hurt. But as an engineer, when you go to site, you have to keep those things in mind. You're not rated to play with power. You're rated to design the system so that it's safe for users, or for electricians and end users of the power. But that concludes the first lecture. I was supposed to be 45 minutes. I ended up an hour and 15, so I'm going to get to go to the editing floor. But I appreciate you for stopping by. I've got 2 more lectures coming up. Same topic, but they're part 2 of 3 and 3 of 3, and they'll go into more about PPE, more about arc flash, and then of course the third one is the technical demonstration, where I'll show what happens in an electrical burn to a person's body. And yeah, I appreciate you coming out, appreciate your time. With my office door being closed, I'm getting really hot in here, so I'm going to shut down. And thank you very much for those that did stop by and say hello. I appreciate you.